So in the last couple of videos, we've been doing trend forecasting. Now, we talked about how to check and see if your trend forecast is a good pick. We looked at R squared, the coefficient of determination. We looked at how much it made sense in terms of the forecast into the future. We looked at how complicated the models are and being able to explain them to our stakeholders. But whenever you do forecasting, what you want to do after the fact is measure your forecasting error. How accurate was the forecast when you made it before the events happened in the future? And then after those events happened, how far off was your forecast? We want to measure the accuracy of our forecast. There are different ways to measure the accuracy of your forecast. There's what's called mean absolute deviation, mean square error, and mean absolute percent error. And if you check out the other videos, we've shown how to calculate those using Excel or by hand. Well, let's look in this video on how to do that in Python. So if you're wanting to measure forecasting accuracy in Python, you can go to, let's just pull it up here, drstephpowers.github.io/management in Python, so mgmt-in-python. And we've been working through in our videos this forecasting Python workbook here. So click on forecasting, it opens up a GitHub site. Click into Google Colab, that's this little button right here. And once you do that, then you will want to log into your Google account and you'll want to make a copy to your drive so that you can run the code and amend the code. And if you're doing this for one of my classes, then please save your work. That way when you share the file with me, it has your additions and not just the original document. All right, so let's take a look at calculating measurement error. So there are different ways to calculate measurement error, forecasting error, the mean absolute deviation, the mean square error, the mean absolute percent error. All of these are founded in measuring forecasting error as actual minus forecasted. So we need a number of periods where we have the actual data and our forecasted data, and then we can look at on average, how do we do? So the mean absolute deviation looks at the absolute value. So it takes out the positives and the negatives and simply looks at on average, how far were you from the actual. The mean square error squares the difference between the actual and the forecasted to accentuate those particular data points that are far off. So whereas the mean absolute deviation treats them all equally in terms of weight, the mean square error puts emphasis on a single forecast that might be off by quite a bit. And then we have the mean absolute percent error, which takes the absolute difference between the actual and the forecasted, turns that into an average percentage. And the benefit of this is that we don't have to compare it to anything. The mean square error, the smaller value is better. The mean absolute deviation, a smaller value is better, but you have to compare it to some other forecasting method. With mean absolute percent error, we don't have to compare it to anything because 100 minus the mean absolute percent error is your percent accuracy. So you don't have to compare multiple methods with the mean absolute percent error. So how do we do this in Python? Well, in Python, we're going to need the import pandas as PD and import numpy as NP because we're going to be manipulating numbers and data. And then the other thing that we're going to need is we're going to need our forecasted values from the different methods that we've gone through. So for example, when we did our linear forecasting method, we found that when the periods were 9, 10, and 11, the forecasted values were 85, 88.8, and 92. So we need to pull those numbers so we can copy those. We need to pull the numbers from the polynomials. For example, when we did our polynomial of degree 2, we had forecasted for periods 9, 10, and 11, 98.89, 111.7, 126. And for 3 periods, it was 81, 71, and 51.6. We can pull the forecasted values from the logarithmic. It was 77.6, 78.7, and 79.69. We can also pull the forecasted values from our exponential, 85.6, 90, and about 95. So in order to calculate our measurement error, let's take the predicted from the exponential, and I'll just paste them in here. And the predicted, oh, how about I go to the one where I'm signed in? So you notice that because I'm not signed in, it won't let me run the code. So make sure you sign into Google and then save yourself a copy. So let's go into the one where I'm logged in. All right, so let's paste in the predicted values for the exponential, predicted values for the logarithmic, predicted values for the polynomial of degree 3 and polynomial degree 2, and the linear. So all I did was just copy these from earlier in this document, and we're just giving them a name. Now we need to compare those forecasted values to actuals. So let's assume that periods 9, 10, 11 pass, and the complaints are 75, 70, and 73. So let's put those in. And to make it easier to see, I'm just going to create a data frame using my list zip that we've talked about before. And I'm just going to take actual and then linear, then poly 2, then poly 3, then log, then exponential. And I'm going to give them names, actual, linear, poly 2, poly 3, log, and exponential. And I'm going to turn it into a table. And I'll just call this table ME for measurement error. And have it output the information. So I can see it all, right? So I can see it at a quick glance in table 4. Now, when it comes to these forecasting error methods, mean absolute deviation, mean square error, mean absolute percent error, they aren't formally defined in Python. So we're going to use Python definitions to write out the formulas, and then what we can do is we can then apply those to all the different forecasting methods. So let's define MAD, which will need a true value for y and a predicted value for y. And then it's going to return the average of the absolute value of the true minus predicted. So notice all we've done here is just taken the actual minus the forecasted, take the absolute value of that, take the average of that. So you don't actually have to recreate the formula. It's already been done for you. So if you're doing this with your own data set, simply copy this definition as is, and we run it. Which means we can then call this definition for our different forecasting methods. So it needs, when you call MAD, it needs to have the actual and it needs to have the predicted. So let's find the mean absolute deviation when we compare the actual complaints to those complaints that were predicted using the linear model for periods 9, 10, and 11. When we do that, we get a mean absolute deviation of 16. Well, great. What does that tell us? Well, it means on average, the complaints are 16 off from what the linear regression says they should be. Is that good or bad? Well, you need another model to compare it to. So let's do MAD, comparing the actual to the polynomial of degree 2. Notice here with the polynomial of degree 2, the MAD is 39.6. This tells us the linear model was a better predictor of periods 9, 10, and 11 than the polynomial of degree 2, if reality really is that the actuals are 75, 70, and 73. If the actuals end up being some other numbers, then this may not be the best model after all. So it is highly related to what the actual data turns out to be. Let's check the other ones. So let's look at polynomial of degree 3. Notice that this one has a even smaller MAD than the linear model. We can do the same thing with the logarithmic. Notice the number is even smaller. So this would suggest the logarithmic function is a much better model for forecasting number of complaints at our organization than the other models. So as we check this against the actual data, this then helps us in the future. If we're going to model complaints again in the future, but the logarithmic model is probably the best one for how our organization operates. We can also do the exponential. You can see it does not fit very well, second only to the polynomial degree 2 in terms of the worst fit. So mean absolute deviation treats all of the forecasting error, the difference between actual and forecasted, equally. And so in that case, the best model is the logarithmic. Now we can look at other methods for forecasting accuracy. So let's look at mean square error. This puts an emphasis on when even a single forecast is quite off. So instead of treating them equally, it emphasizes even when there's a small handful of forecasts that are way farther off than everybody else. So let's go back in. The mean squared error is already defined by the sklearn.metrics mean squared error command. So we can, from sklearn.metrics, import the mean squared error, and so we don't have to find the calculation ourselves. So here we're going to do mean squared error, and then you need to give it the actual, and you need to give it your forecasted value. So these are columns from our measurement error table, and so that part in quotes is the name of the column. So when we run this for the linear, we get a mean square error of 277.75. Is this good or bad? Well, that depends on what the other models provide. So we would check this with the polynomial of degree 2. Notice the linear model fits better than the polynomial degree 2. You can do this with polynomial degree 3. The polynomial degree 3 fits better than the linear or the polynomial 2. And we can check the logarithmic, and we can check the exponential. So notice in this case, the best fitting model is the logarithmic. This matches the MAD. That is not always the case that they match, because the MSE will flag when there's one forecasted value that's way far off compared to the rest, and the MAD would tend to kind of ignore that or cancel it out. So while most of the time the one that they report is the best is the same between the two, it doesn't have to be. It depends on if there's just a small number of forecasts that are just really, really far off. The last method we want to look at for forecasting error is the MAPE. MAPE, you'll recall, is the mean absolute percent error. It takes the absolute value of the error, difference between actual and forecasted, turns that into a percentage, and finds the average of that percentage. The benefit is we can take 100 minus that to get the percent accuracy. Now, the mean absolute percent error is not defined in Python, so we have to create our own definition. So we'll define MAPE with the inputs of the true value and the predicted value. And then we're going to have it find the absolute value of the difference between the true and the predicted, and divide that by the true. So find the absolute difference and find the percentage, and then find the average of it, the average percentage. And it's going to return that value. So you don't have to worry about writing out that formula. If you're doing this for your own data set, simply copy that definition, run it, and then you can call it with your own data. So here we have the measurement error table. We're comparing the actual and the linear predictions, and we get an MAPE of 22.325. What this means is that this linear model has just under an 88% accuracy. So 100 minus 22 gives us the percent accuracy. Compare this to a polynomial of degree 2, which is less than 50% accurate. Polynomial of degree 3, you can see, has an MAPE of 13.4, 100 minus 13, right? Get close to 87, so we're looking at 87% accuracy. MAPE for the log is 8, so almost 92% accuracy with that logarithmic function, based on the fact the actual data, remember those actuals, if I go back, where are we, actuals, were 75, 70, 73. So you can see why a logarithmic might make sense if it's kind of plateauing around 75, 73. We check the log. Let's try the exponential. The exponential has an MAPE of 24. 100 minus 24, we get an accuracy close to 75% there. So in this case, the logarithmic was the best forecasting method given the complaint data, given that what was happening in our business, and given that we forecasted periods 9, 10, 11, and what actually happened.